noise, vibration, and harshness. NVH is often used to collectively express these three phenomena that the driver experiences while driving. These phenomena are not only unpleasant to the driver and passengers, but also make them worry whether something might be wrong with their car. That's not all. Problems involving NVH are often unwelcome to technicians who think they are difficult and time-consuming to repair. But that is not necessarily true. If you know the principle of vibration, which is to say, if you know what vibration is, and if you understand the generating mechanism of vibration and noise in vehicles and how to prevent these, and if you familiarize yourself with basic troubleshooting procedures, NVH is not as difficult to fix as you might think. In this video, we will learn about the principles of noise and vibration generation and how to troubleshoot NVH problems step by step. We will use simple models to demonstrate the nature of vibration, which just means the rapid oscillation of an elastic solid or fluid. The number of such periodic movements, or cycles, per second is called the frequency. Frequency is expressed by the unit hertz. For example, 1 hertz is equal to 1 cycle per second. These systems, each consisting of a weight and a spring, are called vibrating systems. Now we will put another lead sinker of the same weight as the first on a second, stronger spring. You will notice that the weight oscillates faster on the stronger spring than on the weaker spring. This time, we will put 2 weights on one spring and 1 weight on the other. Both springs are of the same strength. You will notice that the lighter weight oscillates faster than the heavier weight. When you compare these vibrating systems, you will find that the frequency of the vibration varies depending on the strength of the spring and the heaviness of the weight. The frequency at which a particular system oscillates or vibrates is called the natural frequency of that system. Now, we will do some experiments using a vibrating system consisting of a spring and a weight and an electric drill. The spring and the weight are now oscillating at the natural frequency of the vibrating system. Now, let's see what will happen when this drill rotates at a speed that is different from the natural frequency of the weighted spring. You will notice that turning on the drill reduces the amplitude, or size, of the oscillation of the spring. Now, we will increase the speed of the drill until the frequency of the oscillation that it produces reaches the natural frequency of the vibration system. You will notice that the amplitude of the oscillation increases. When a system is vibrating at its natural frequency and a vibration of the same frequency is added to it, the amplitude of the vibrations becomes larger. This phenomenon is called resonance. The source of a vibration, such as the electric drill in this example, is called a vibrating force. A vehicle has a number of components that can be vibrating forces. We will show you some of them now. When a car is parked in the same place for many days or weeks, there will be a flat spot at the bottom of the tire. This flat spot will cause the wheel to vibrate each time the tire turns. This can, in turn, cause the body of the vehicle to shake. An unbalanced propeller shaft also causes vibration each time it turns. This can cause a droning or humming noise called booming, as well as vibration when the car is running at a high speed. The engine, too, is a major source of vibrating force. The torque fluctuations due to combustion in the engine create a vibrating force. This may also cause booming. We will now study the mechanism by which these vibrating forces lead to vibration and noise. For this purpose, we will study how the engine causes booming. The owner of this car complained that booming is heard when the engine is running at about 4,200 RPM. The engine vibration causes the exhaust pipe to vibrate. The vibration of the exhaust pipe is transmitted to the body if the exhaust pipe support is not fitted correctly. The body begins to vibrate, causing the air to vibrate also. This vibration is heard in the form of sound or booming by the driver. Let's sort out the elements of the mechanism of this booming. In this case, the engine vibration is the vibrating force, and the exhaust pipe forms a resonance system. The exhaust pipe support forms a vibration transmission system. And the body is the vibrating element. The vibrating element causes the air to vibrate, and the vibration of the air is transmitted to the driver's ears as the booming. Sorting out the various elements of a problem is very important for troubleshooting, and you should always analyze problems in this way. Vibration and noise can be prevented, as we will see next. Generally speaking, vibration can be prevented if you eliminate one of the elements in the mechanism of vibration. If you eliminate the vibrating force, the resonance system, the vibration transmission system, or the vibrating element, you can minimize vibration. A variety of designs are incorporated into an automobile to prevent or minimize vibration. Let's review some of the designs that are aimed at attenuating the vibrating forces. The vibration of the engine, due to the reciprocating movement of the pistons, for example, is prevented by the use of balance weights on the crankshaft. The propeller shaft, the tires, and other components that turn at high speeds must also be well balanced. A wheel balancer is used to balance the wheels when new tires are installed. All of these measures are aimed at attenuating the vibrating forces. A second way vibration can be prevented is by eliminating resonance. A weight is sometimes attached to the accelerator pedal to change its natural frequency in order to prevent resonance. This type of weight, that is, one that is attached directly to a vehicle component, is called a mass damper. When a weight is attached to a component indirectly via a rubber pad or cushion, it is called a dynamic damper. The third way to prevent resonance is by modifying the transmission system. For example, rubber or other vibration-suppressing material is inserted between the engine and the body to prevent vibration from being transmitted to the body. Rubber O-rings are also used between the exhaust pipe and the body for the same purpose. The fourth way to prevent vibration concerns the vibrating element itself. For example, the floor is covered with asphalt sheeting, or resin sheets are inserted between steel panels to suppress vibration. These panels are called sandwiched damping panels. As you can see, the principles of vibration are not so difficult to understand after all. Now, based on these principles, we will study how to troubleshoot NVH problems. An important thing in troubleshooting is to forget all your preconceptions about vibration and to listen to and analyze the customer's complaint accurately and objectively. A diagnostic chart may be helpful. If possible, you should also get into the car with the customer, test drive the car, and confirm the problem in some detail. More importantly, you should find out the vehicle speed and engine speed at which the problem occurs, as well as other relevant factors, and identify the characteristics of the vibration and noise as accurately as possible. When you have all the necessary information, it should not be too difficult to identify the source of the vibration. In addition, you should sort out all the elements of the mechanism of the vibration and noise and decide which element you need to remove in order to suppress them. We will now study actual troubleshooting using two cases as examples. One of the two cases concerns body shake. The first step of troubleshooting is test driving the car to confirm the phenomenon. You need to know the relationship between the body shake and the vehicle speed. In this case, you first begin to notice vibration when the vehicle speed rises to approximately 80 kilometers per hour, and the vibration increases as the speed increases to between 90 and 100 kilometers per hour. You also need to know the relationship between the body shake and the engine load. You accelerate, cruise, and decelerate the car repeatedly, but the vibration seems to be unrelated to the engine load. The shift lever position and the engine speed often have effects on vibration. In this case, the shift lever position and the engine speed seem to be unrelated to the problem, as the vibration is still felt when you move the shift lever or change the engine speed. Now, let's summarize all the test results. The test results indicate that the engine load and the engine speed are not related to the problem. The shift lever position is also unrelated to the problem. You can now conclude that the vibration is not caused by the engine or the transmission. So we need to look for some other factors. We know that the vibration increases as the vehicle speed increases. It appears then that you should suspect a component whose rotational speed increases as the vehicle speed increases. It could be the propeller shaft, the differential ring gear, the drive shafts, or the tires, or some combination of these. The next step is to find out exactly which of these components is responsible for the problem. There is a good way to identify this component. Since any of these components could generate a vibrating force, let's calculate the frequency for each component at 100 kilometers per hour. We will begin with the tires. The rotational speed of a tire per second is calculated according to this formula. When the vehicle is running at 100 kilometers per hour, it travels 28 meters in a second. Assuming that the radius of the tire is 0.3 meters, the tire circumference will be 1.9 meters. Therefore, we can conclude that the tire turns 15 times per second. If a tire has become unbalanced or run out, it will cause a 15 Hertz vibration. The same can be said about the drive shaft or the differential ring gear. What about the propeller shaft then? The rotational speed of the propeller shaft is calculated according to this formula. As you remember, the tire turns 15 times per second in this case. Since this vehicle has a differential gear ratio of 4:1, we can draw the conclusion that the propeller shaft turns about 60 times per second. For this reason, if the propeller shaft is unbalanced, it will cause a vibration at the frequency of 60 Hertz. In addition, if the propeller shaft has an excessively large joint angle, it will cause 2 excessively large torque changes per rotation. This will cause vibration at a frequency of 120 Hertz, or twice that of the propeller shaft. As you will realize by now, you can identify the vibrating force if you know the frequency of the vibration about which the customer is complaining. A vibration frequency analyzer is used to measure the frequency of a vibration. A vibration frequency analyzer has a pickup probe which is attached to the vibrating part in question. The frequency of the vibration is indicated on the analyzer. You can read the measurement by moving the cursor on the screen. In this case, the frequency reading is 15 Hertz. This indicates that the vibrating force is generated by the tires, or by other components that are turning at the same speed as the tires. If a vibration frequency analyzer is not available, there are other methods that you can use to estimate the parameters of a vibration. All you need is your hand and an intuitive knowledge about the most commonly occurring frequencies. For instance, this component is vibrating at a frequency of 15 Hertz. If you touch it with a screwdriver, you can hear and feel it quite easily. An impact wrench generates vibrations of a similar frequency. This rearview mirror is vibrating at a frequency of 60 Hertz. It is moving faster than your eyes can follow. But if you touch the mirror, you can feel its vibration. A bench grinder has a similar frequency, about 50 to 60 Hertz. If you touch the grinder, your hand soon becomes numb. If you train yourself properly, you will be able to distinguish between different frequencies without using a vibration frequency analyzer. Now, we will return to troubleshooting the problem of vibration at 15 Hertz. We will start with inspecting the tires, because tires often cause body shake at high speeds. We will refer to the NVH diagnosis manual as we inspect the tires. Before we begin the inspection of the tires, we must check the tires and wheels visually, the steering linkage, the suspension system, and other related components. If everything is normal, we check the clearance between each hub and wheel. The standard clearance is less than 0.1 millimeter. This wheel seems okay. We will check the tire runout next. Before doing this, be sure to dry the car for about 15 minutes to eliminate the effects of any flat spots. The maximum allowable lateral runout is 1.2 millimeters. This tire seems okay. Let's check the radial runout next. The maximum allowable radial runout is 1.0 millimeters, but the reading here is much larger than that. This could be the cause of the vibration. Let's check the radial runout of the wheel also. The wheel runout is not zero, but it is within specification. In a case like this, the radial runout can be corrected by conducting phase matching between the tire and the wheel. If you move the thickest part of the tire to the point where the center of the wheel is closest to the rim, the radial runout will be reduced. This procedure is called phase matching. As you can see, the runout has been reduced. To phase match the tire and wheel, we divide the tire into 12 equal divisions like this. Then, before starting the measurement, set the dial gauge to 0 at location 12. Next, record the amount of runout at each point. The results will look something like this. The outer line indicates the radial runout of the tire, and the inner line indicates the radial runout of the wheel. As we said before, if you move the thickest part of the tire to the point where the center of the wheel is closest to the rim, the radial runout will be reduced. Let's check the results of the phase matching. The measurement now reads well below the standard value of 1.0 millimeters. You need to do a similar check for all of the other tires. Wheel balance is also an important component of the vibration that occurs in automobiles. So before taking the car on a final test drive, be sure to check the wheel balance on both an off-the-car balancer and an on-the-car balancer. The second case of troubleshooting that we will look at is booming, which is, as you will remember, a droning sound that is very unpleasant to the ear. The first step is test driving the vehicle as you did when troubleshooting body shake. As a result of the test drive, we find that only the vehicle speed is related to the noise. Also, we find that the noise is first heard at a speed of 80 kilometers per hour, and that it reaches its peak at a speed of 90 kilometers per hour. These findings seem to indicate that the noise is caused not by the engine or the transmission, but by components whose speed varies directly with a vehicle speed. The next step is to calculate the frequency of the vibration of individual components at a vehicle speed of 90 kilometers per hour when the noise is most noticeable. Now we will measure the frequency of the booming using a sound meter and a frequency analyzer. The sound meter and the frequency analyzer are connected like this. According to the analyzer, the frequency of the noise is 60 Hertz. This frequency corresponds to the frequency at which the propeller shaft will probably vibrate if it is unbalanced or run out. This indicates that you should suspect the propeller shaft more than anything else. You may not have a sound meter or frequency analyzer at hand, but you can always use your own ears after some training. For example, the frequency of this sound is 60 Hertz. It is similar to the booming in question. A sound of the same or similar frequency is also heard from a bench grinder. This is a sound whose frequency is 120 Hertz, or twice that of the previous case. A sound of a similar frequency is produced by a cooling fan motor. The booming produced by the engine sometimes has a similar frequency also. As the frequency increases to 1 kilohertz, you will hear a sound like this. A sound of similar frequency is heard, for example, along with the test pattern on a TV screen before and after the day's broadcasting. Transmission or gear noise sometimes causes a similar sound also. If you train your ears by listening to sounds of different known frequencies, you will be able to differentiate frequencies without the help of an analyzer. We will now return to the case of the booming about which the customer complained. It appears that the noise is caused by something that rotates at the same speed as the propeller shaft. Or perhaps it is caused by the propeller shaft itself. We will check the balance of the propeller shaft, as it seems the most likely cause of the vibration. Please look in the NVH diagnosis manual to find the detailed inspection method to be used. Here we will only show the main techniques used in the propeller shaft balance inspection. Actually, there are 3 methods that can be used to check the balance on the car. First, we will check the balance using a vibration analyzer and some trial weights. Before you can begin the inspection, you need to jack up the vehicle, check the installation of the propeller shaft, and check the surface of the shaft for damage. Then, put 4 marks, 90 degrees apart from each other, on the propeller shaft like this. Now attach the pickup probe of the vibration frequency analyzer here. This inspection requires 2 persons. One person stays inside the car and operates the engine to reproduce the complaint. When the booming is heard, this person sounds the horn to signal the other person. When the second person hears the horn, he checks the vibration level reading on the frequency analyzer. The reading is 0.17 in this case. Now put a trial weight onto the propeller shaft where it is marked number 1. You may use a hose clamp as a trial weight. The screw of the clamp serves as the trial weight. The weight of this screw is 17 grams. We will measure the vibration again with the trial weight attached. We must repeat the measurement at all 4 points. Next, we draw a graph using the measurement data. The length of each arrow corresponds to the vibration level at each point as indicated on the analyzer. Now we draw bisecting lines perpendicular to the arrows from 1 to 3 and from 2 to 4 and determine the intersection point. The direction of the intersection point from the center of the graph is the direction of the imbalance. In other words, an extra weight exists somewhere along the shaft in this direction. The amount of imbalance is determined by this formula. When we calculate the measured data according to this formula, we find that the amount of imbalance is equal to 10 grams. Because the results indicate that an imbalance of 10 grams exists in this direction, we need to add the same amount of weight on the opposite side of the shaft in order to eliminate the imbalance. Please refer to the NVH Diagnosis Manual for details. The propeller shaft balance may be checked by other methods also. It can be determined by a feeling test as you move a trial weight from one point to another. Or it can be determined using a propeller shaft balancer. You will find more details about this method in the NVH Diagnosis Manual. The imbalance may be corrected by using balance pieces and weighted bolts like these. Now the repair is complete. The car is now ready for a test drive. In this video, we learned about vibration, the mechanism of vibration and noise associated with vehicles, and methods to prevent them. In addition to these principles of vibration, we learned about troubleshooting for two common cases. Please remember two important rules of troubleshooting. 1. Identify the symptoms of the problems accurately by listening to the customer and by test driving the vehicle yourself. And 2. Search for the vibrating force and vibration generating mechanism in accordance with the principles of troubleshooting. We hope that this video has been useful to you. Please refer to this video and the NVH Diagnosis Manuals at all times to correct NVH problems accurately.